right, the only announcement I know about now, things should be getting back to normal, kinda. The only thing is today, my office hours are 3:15 to 5:15, normally on Mondays and Wednesdays. Today, sometime shortly after 3:15, 3:30, before 4 o'clock anyway, I'm going to have to run down to Pet Boys Auto Place, just real close here, because my car died completely and is sitting in their parking lot, and I'm having someone come and tow it away today. I'm getting rid of a car. I'm in a rental car right now, so I will be out of the office then. They have a window that they can come, and it's 5:15 is too late in that window, so I've got to be down there before 5:15. In fact, they want me on the earlier end of it, so I'll be out of the office hopefully no more than 15 minutes, because it's real close. All I have to do is get my tag off the car and sign over the title to them and get them checked. And that shouldn't take too long. Give them the keys, okay? But I've already unloaded the car, gotten all my stuff out of it, except the tag. I got to do that today. So I will not be in the office full 3:15 to 5:15, but after the first few minutes, hopefully I'll be back. All right, the rest of the week, as far as I know, my office hours should be kind of normal. I hope whatever normal is anymore. Okay. I don't know what. You don't see this. Do you want to change the color scheme to improve performance? Now, how can color scheme improve performance? That makes no sense to me, but anyway, I clicked off of that. Okay. Now, any questions on anything we've covered up till now? All right, we're still in Chapter 7, Techniques of Integration, and 7.5, the method of partial fractions. This has taken a bit longer than I had thought it would, but it isn't. It is a fairly complicated technique. And on the one hand, it's pretty simple, but it takes a lot of steps to get there. Okay, no questions before we get started? Okay. Then we're on example 6 on page 403, about the middle of the page. Here is the request. Let me get my pen activated. Okay. The integral of 4 minus x over x times x squared plus 2 cubed dx. No, that's a squared. I was going to say, wow, they hit you with a cube. They just hit you with a square. I can't read very well. Yeah. All right, what do you suggest we do to solve that? Okay. Second. Okay, do the ABC thing. What is this doing, this stupid? Do you want to change the color scheme? Goodness gracious. Okay. So we're going to take the 4 minus x over x times x squared plus 2 squared and split that up somehow, the ABC thing. Okay? What would be your rendition of the ABC thing? A over x, good start. Plus, okay, let's not use A. Yeah, okay. B over what? X squared plus 2. Now, does anything seem a little problematic there? Okay, yes, that may be the problem, but the problem's in the x squared is there in the problem. Can't change that, but your numerator. Is what? Bx plus c. Okay, I didn't hear the x. Yes, you have to have it 1 degree less than what the denominator is. bx plus c times x squared plus 2. But you got another one of those, so what are you going to have to do? Plus, is that dx you said? Yeah. Okay, dx plus, okay, plus e over x squared plus 2 squared. Yes, that's what we do when you have repeated factors. We just keep repeating a similar numerator, but increase the powers till you reach whatever we reach here. And always you have your numerator being 1 degree less than the denominator. When you have a irreducible quadratic factor, the numerators will be linear. Okay, so there's your ABC thing, right? Now, what do we do next? Second?
What page were you in?
What page? 403, 403. Okay, and what is the LCD? Okay, so let's do that numerator. 4 minus x over x times x squared plus 2 squared. Multiply that by x times x plus x squared plus 2 squared. Okay, equal a over x times x squared plus 2 squared plus bx plus c times x squared plus 2 squared over x squared plus 2 plus dx plus 3 plus e times x squared plus 2 squared over x squared plus 2 squared. That's what takes so long about it, is writing everything out. Did I do it right? Yeah. Okay? Now, what happens to the left of the equal sign? Yeah, the x's go out and the x squared plus 2 squared goes out. So you're just left with the 4 minus x. Okay. To the right of the equal sign, the first term, what happens? The x's go out and you're left with a times x squared plus 2 squared. In the second term, one of the x squared plus 2 goes out, and you're left with a bx plus c times x times 1x squared plus 2. Okay? And in the third term, yeah, that denominator goes into the squared term squared, and that gives you a plus dx plus e times x. Do I have it right? So the good news here, you've lost all your denominators. That's why we did that. Now what do we do? Second, find those parameters A, B, C, and D, and E. How would you suggest we approach that? It's wanting to change color again. It's such a pain in the neck. Okay. Second. Yes, let x equals 0. That's the only thing you can eliminate that way, so we'll do let x equals 0. Okay, what's on the left? What would you have? 4 is equal to 4a. That's all, folks, because that one goes to 0 and that one goes to 0. So guess what? A is equal to 1. Very good. And that's all we can do easily. The rest of them we're going to have to do our longer process. So it's going to be 4 minus x is equal to x squared plus 2 squared, right? Because a is 1, plus, all right. I want to go on and do all my multiplication if we can. Can we do it all at once? Okay. So let's start with our leading terms. Bx times x would be bx squared times x squared would be bx to the 4th, right? Okay with that? Okay. So there's a bx to the 4th. All right. Now let's do those that are going to be cubes. That would be a bx times x. No, that's not going to give us any. The only one that would be cubed will be cx cubed. Right? Huh? Yeah, you want to do that first? Okay. If you multiply the x by either one of those, you're still going to have binomial. Then you can do foiling if you want. You rather do it that way? Huh? Yeah, it's probably less confusing. Let's put it that way. So let's do that. Let's do a little scratch work. And what I'm going to do is erase some stuff that I hope we won't need anymore. I hope we won't need this line anymore. Do you think we will? Because I think we've gotten everything out of it we can. So let's erase this line. Otherwise, I'm not going to have room to do much. Okay. Okay, I think I got it all erased. So we're going to multiply this, and this will be, you want to multiply the x times the bx plus c, or you want it by the other one? Huh? The other one, okay. So you want bx plus c times x cubed plus 2x. Is that what you want? Okay, now let's FOIL that. What do we have? Bx to the 4th. Now, I'm going to do it this way. I'm going to misspell FOIL, okay? Cx cubed, right? Plus Cx cubed, okay? Then let's do the outer, and that's going to be plus 2bx squared. Is that what you want? 2bx squared, and then the last is going to be plus 2cx. Is that what you wanted? Okay. That's a little neater, isn't it? Huh? Yeah. Okay. So that's bx to the 4th plus cx cubed plus 2bx squared plus 2cx. All right? And the last term's pretty easy, isn't it? What's that? Plus dx squared plus ex. Got it. Good deal. Now, one more thing I think we need to do. I'm going to go up above and do it what is x squared plus 2 squared? What is that one? First term we have there. X to the fourth plus 4x squared, perfect. 4, okay? It's so tentative of that. Okay, what I'm going to do to save room and to keep from having to write all that again, I want to take this out and put that in. X to the fourth plus 4x squared plus 4. Then plus this other stuff, right? Are we ready to go? Now, let's start with the highest power over here, our x to the fourth. Here we have 1 plus b, right? 1 plus b, x to the fourth is equal to how many x to the fourth over here? 0. So 1 plus b is equal to 0. What does that tell you? Huh? Okay. Quit doing this! You don't see it, but it just pops up and messes up. Here we have an x to the fourth term, and here we have the x to the fourth term. That's all the x to the fourth terms we have, right? What x to the fourth term do we have on this side? 0. Yeah. So we have 1 plus b is equal to 0, right? Okay? All right. So 1 plus b is equal to 0. Let's write that up here. 1 plus b is equal to 0. What is b equal to? B is equal to -1. All right, that's done. So we got taken care of our x to the fourth. Okay. You want to go to the x cubed terms next? Okay. Here I only see one x cubed term here. Don't you? Okay. And how many do we see over here? 0. So guess what? C is equal to 0. All right, we got another one done. C is equal to 0. So you got A is equal to 1, B is equal to -1, C is equal to 0. Okay, that's taken care of. All right, we want to move to the x squared terms. Okay. What do you notice over here? We got a 4. Yeah, but b is next was so 4 minus 2 plus d is equal to what? That was 4 minus 2 plus d is equal to 0. Is that what we had? Okay. And this would be 2 plus d is equal to 0. So guess what d is? D is equal to -2. All right. So we got A, B, C, and D. All right. I want to go to my, why not, let's just go straight to the x term, right? Okay, over here, what do we have? -1 over here. I'll write it down here. -1 is equal to what's next on the right hand side? 0. 2c is 0, so that's gone. Plus e is equal to e. So guess what e is? -1. All right. That's looking pretty good, isn't it? Buy that? All right. You've got all 5 of them now. You want to just check and make sure the last one makes sense? No. Okay, he's confident. We got him right. Okay, here we have a 4 is equal to 4. Huh. Yeah, 4 is equal to 4. That's right. Okay,
so
that wasn't funny.
E equals 1 because of the x on the left side?
Yeah, your x term here coefficient here is a -1. And then that's the only x term over here. So e's got to equal -1. Got it? Okay. So, I've got another stupid message here. Okay. All right. So what I'm going to do is collect all these at the bottom. Okay? So I think what I'll do is erase this. I don't need that anymore. We've already used that. And this. Alright, and we probably don't need this either. I'm real tempted to write these equals -2 down at the bottom, but I think we got room without it. Alright, now your integral. Instead of your 4 minus x over blah, 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 we're going to put a over x. What was your a? 1. So those would be dx over x. Now, why did that introduce a line like that? I don't know. This thing's going nuts. dx over x. Okay. Plus the integral of, what was your b? -1. So that's going to be a minus x, and what's your c? 0. And that's over x squared plus 2, right? dx. See what we're doing? Okay. And then the next integral is going to be, what's your d? -2 minus 2x plus your e. What's your e? -1 over x squared plus 2 squared. Okay, dx. All right. I think, therefore I am, we have done all we can with what we got. So finally I'm going to erase this stuff that's in the way. Okay, is that all right? I think we used this. I hope we used it rightly, so I won't need to come back to it again. This is just so I can see and tell what I'm dealing with here. Okay? But you've got it all written down, so we can come back to it if we need to, right? Okay, I'll stop that right now. We might need it later. What's the first one integrate to be? This will be log x, absolute value x. All right. Now, what's that next one integrate to? What would you do there? Okay, that sounds like a wiener. Okay. All right, that's done. Now what? Exciting stuff, isn't it? How would you solve that second integral? Right there. Got the -1 here. That was a nice one. Substitute. What would you substitute? Say again? Let u equal that? Okay, I'm going to write it up here. Let u equal x squared plus 2. Then du is equal to 2x will be the first part of it.
2x
dx. Very good. Do we want a 2x dx? We don't have that. Yeah, we only have an x dx, so let's divide both sides by 2. All right. Now our substitution here will be minus 1/2, right? Because the du will be that. The integral of du, x du, the 1/2 up front, over u, right? Is that right? Okay. All right. Now, what else? What you want to do with that third one? I'd bring a negative out too, so I'm going to go back and do that the easy way by making that minus, and that plus, and the next one plus. Okay? Now, what do we do here?
You have to do the little AP thing again?
I sure hope not. Okay. Actually, I mean, it's not a bad idea, maybe. And I guess you could. I keep getting these stupid messages. Okay. So what else might we try to do? Okay, I'm going to show you a little trick. Is that okay? Don't mind a little trick. Okay. When you have a binomial in the numerator, let's do this. Let's make this a minus the integral of 2x over x squared plus 2 squared plus, and that's dx, plus, we'll make that a minus. Okay. The integral of dx over x squared plus 2 squared. Okay. Now I think I'm going to need room beneath, so can I go on and erase all this below? Gonna be okay? Y'all got it all down if we do need to recall any of it. That's the thing about this technique. It really dredges up, and you have to use just about everything you've ever done before. Possibly, anyway. Wow. This is so slowly erasing. Okay. Did y'all see it erase while I was doing that? Okay. Pretty weird, isn't it? Okay. Log x is okay. Minus 1/2. What's that next one? Log u. But what is u? Huh? Me? Is that what you said? Uh-huh. All right. A comedian. Okay. All right. You get a few points back for that one. Okay, what's that? X squared plus 2. Absolute value. Actually, do we need an absolute value bar anymore? Because x squared is always positive, and add 2 to it is always positive. That. Just do x squared plus 2. If I could write, okay? All right, now we got something that looks sort of like we did before, don't we? Yeah, let's do a substitution. What do you think we'll substitute? Okay. I like it. And then the u is still 2x. And this one we actually do have a 2x up there, so we don't need to divide by 2. So I'm going to use the same thing we had before, except we don't have to divide by 2 now, do we? Because we already got a 2x dx. Okay? So what now is this integral? Minus the integral of du over u squared. Okay? Now, kind of the bad news here, what are we going to do with that last one? I'm listening. Erase it. Okay, I know what you're thinking. Okay. Is what? New. Okay. I'm going to do this. See if it'll quit asking me. Okay. All right. Do you remember a couple of sections ago we had something that dealt with forms that had something like this in it? Oh, yeah. Okay. We probably did that. What was that lead to? Huh? It's a trig substitution, exactly. And what would that trig substitution be? Well, now this time we did it slightly differently. Let x equal, whereas before we'd set a u, this time we're letting the x equal, second? Okay, square root of 2 tangent. If that had been a 4, that would have been, it's of the form x squared plus a squared. But here, 2 isn't, okay. So square root of 2 tangent theta you want to use? Yeah. Okay, I thought you did. Okay. Now, we got to do our maneuvering with that. We maneuver a couple of different ways. What's one? Then dx is equal to remember that one? I'll do the first part, root 2. No, that's 10. That's secant. Secant squared. Derivative of tangent is secant squared. Okay? Secant squared theta. D theta. All right. All right. Now, is it worth doing all the squaring and adding to and dividing and all like this, or can we go straight to the picture and maybe get it to work? If we went straight to the picture, this would say x over root 2 is equal to tangent theta, wouldn't it? Going back up here, if x is equal to root 2 tangent theta, let's just divide both sides by root 2, and then we have x over root 2 is equal to tangent theta, right? Let's draw a little triangle with that. Well, we may still have to do all the other stuff, But let's see. So let's draw that little triangle. Okay, here's the theta. And if tangent theta is equal to x over root 2, where do those go? Opposite is what? Adjacent. Okay. Root 2 is adjacent. What would that make the hypotenuse then? X squared plus the square root of x squared plus 2, right? Okay. All right. Now, what we're doing is with this one right here. Yeah, I think we do need to do all the other stuff. Sorry. I was hoping to get by without it. But it's going to turn out the same stuff, but I think it'll be, well, let's see. All right. Okay. If x is root 2 tangent theta, then x squared is what? 2 times tangent squared theta, right? Okay. And then x squared plus 2 would be 2 tangent squared theta plus 2, right? And factor out a 2, and you have a, I'm jumping ahead mentally. Okay, I don't need to do that yet. Okay, 2 times tangent squared theta plus 1. What is tangent squared theta plus 1? What is tangent squared theta plus 1? Say again? Pythagorean identity. Tangent squared theta plus 1. Say again? Secant squared. Okay, had you already said that? I don't hear well. Oh, okay. 2 secant squared theta. Okay. So that's what your x squared plus 2 is. X squared plus 2 is equal to that. All right. So let's now plug and chug. We have a integral of your dx from up here is root 2 secant squared theta. D theta, right? Over x squared plus 2 is 2 secant squared theta, but you're going to square that, right? So that makes it 4 secant fourth theta, right? All right, so let's start over. We got a log absolute value x minus 1/2, that's ugly 2, log of x squared plus 2, you don't need absolute values there, minus, let's take care of that one. What would that be? Is it alright if I do this? Tell me if this is too confusing. Let's take that out of the denominator, put it in the numerator with an exponent of u to the minus 2 du. Isn't that the same thing? And then what's the antiderivative of that? Yep. Which would then make this a plus u 1 over u, right? Isn't that what you said? U to the minus 1. But what is your u? Yeah, what is your u? Yeah, yes, okay. 1 over x squared plus 2. Right? The minus that you had changed the minus to a plus. Okay? All right, we've got that done. Now let's look at this last one. What we have is a minus, and let's take out the root 2 over 4. Bring that out front. Okay, the integral of, you have a secant squared up here and a secant fourth down here, so that takes us back to a secant squared. So I think I'm just going to erase that and make it a 2 because it's getting so confusing. It's hard to see. Okay. Now remind me, what is 1 over secant squared? Cosine squared. So let's just make that a cosine squared, theta d theta. All right. A little bit of a problem though, Houston. What is the integral of cosine squared? Oh, find that in the chart. You can turn back a few pages if you want to, or turn to the back of your book if you want to. Either place will have them. Cosine squared is, I can't believe it's not right here on top. I can't believe they don't have it under basic forms. They have secant squared and, oh, there it is. It's under trigonometric forms. So it's number 35. Is that what you have? Number 4, okay. You're looking back, I'm looking ahead. What does it give you? Okay, wait. Okay. I don't know where I'm going to write this. I'm going to put minus the square root of 2 over 4. And that integral you said was 1/2 of u. So that would be 1/2 of theta in this case, right? Yeah. 1/2 of theta. So theta over 2 plus 1/4. Now they do sine to u. Happy sine to u until we meet again. No. Let's make that a 1/2 of sine theta cosine theta. Is that okay to do? Oh, does it have the second one? Okay, what does it have? Is that it? Second one. Okay, see, in the back of the book it only has one. So I want to use that one. Is that okay? Okay, because our little triangle here is going to enable us to fill in those blanks. Okay. So, I think, therefore I'm going to erase everything I don't need anymore, which is a lot. I'm going to come up here, we don't need these anymore, I don't think. So I'm going to erase those, we've already used those. I think we got to hang on to the thetas, but let's erase all these because we've already evaluated those. So I need my thetas, so I'm going to hang on to those. And I'll erase these. Not that big difference, but just to get them out of the way. Okay. I probably don't need some of the others, but I don't think I'll even need the room. All right, so let's start plugging and chugging. We have a log, absolute value x, minus 1/2, the log of x squared plus 2, plus 1 over x squared plus 2, minus 2 over 4. It's root 2 over 4. Okay. Times. That's the theta over 2. You know what I'm going to do? I'm going to pull out the 1/2 and make it an 1/8. Is that okay? I'll put this over 8. You all right? Okay with that? See what I'm doing? I already have the 4th here. Most of these are over 2s. It's hard to see that's a 2, but it is. So I'm going to make that an 8. Pull that.
Both of them now?
Yeah, pull both of the 2s out. Okay. Now, all I need now is my theta. Okay? And we almost got there in this line right here. That x over root 2 is equal to tangent theta, right? So therefore, what is theta? Inverse tangent of x over root 2. All right. So there's an inverse tangent, or you could say arctangent if you prefer, of x over root 2. Okay. Now we do plus, okay, this is all still in that parentheses. I'm going to erase some of the rest of this now because I don't think I need this, but I do need my triangle. Okay. It's pretty exciting, isn't it? Okay, plus. We already pulled the 1/2 out. What is sine of that angle theta? That would be x over the square root of x squared plus 2. And what's cosine of that theta? Second? Root 2 over the square root of x squared plus 2. Right? Okay. I think I'm ready to erase my little triangle because it's in my way too. I'll erase everything else down to here. Okay? And I think here's our final answer. Log absolute value x minus 1/2 the log of x squared plus 2 plus 1 over x squared plus 2 minus root 2 over 8 times the inverse tangent of x over root 2 minus root 2 over 8. Now, we got to multiply those two things together, right? What gives that give you your denominator? X squared plus 2. And then the numerator? Yeah, root 2 times x. Well, we have a 2 already. So root 2 times root 2 will just be 2, and 2 over 8 will be 4. So that's going to make this become a 1/4. Is that okay to do? Because I don't have enough room to write anymore. 1/4, and your denominator is, and then it's 1/4 times x over x squared plus 2. One more thing. Plus C. All right. Let's see how we did there, folks. I sure hope. I should have been checking all along, but let's just see. I may have gotten way overconfident here. Log absolute value x, got it. Minus 1/2 log of x squared plus 2, got it. Okay, now they do something a little strange here, but it's okay. You can see we have a denominator here and here are the same, so they just said 1 minus 1/4 x over that denominator. Okay, So let me erase this line below. That was ugly anyway, so I want to erase it. But just because y'all are ugly doesn't mean I want to erase you. I mean, nothing like that. Okay. All right. Now, we're going to combine these two terms. Here we have a plus 1 over x squared plus 2. And here we have a minus 1/4 x over x squared plus 2. X squared plus 2. So that makes this term log absolute value x minus 1/2 log of x squared plus 2 plus, this will be 1 minus x over 4 over x squared plus 2 minus root 2 over 8 times the inverse tangent of x over root 2 plus c. All right, now let's go back and see. I don't know if they put those in parentheses or not, but let's see. Starting over, log absolute value x minus 1/2 log x squared plus 2 plus 1 minus x over 4. They said 1/4 x, however you want to say that, over x squared plus 2 minus, now, I do not know why they like to write it as 1 over 4 root 2. Everything you've ever learned is rationalize the denominator, and since it was already up there, I just kept it up there. That's root 2 over 8. That's nothing different, okay? Times the inverse tangent of x over root 2 plus c. Ha! Done. Don't you wish you had 10 of these on your test? Okay. I'll see what I can do. Okay. Because this uses everything. It uses substitution. It uses trig substitution. It uses partial fractions, of course. It just didn't use integration by parts. But it used just about everything else. Nice. Beautiful problem. Elegant problem, wasn't it? Okay. Now, remember a long time ago, we had, I think is it all right to erase all the stuff here? Okay. Let's pick up and see where they came in. I just started writing. Remember this line a long time ago? This is part of that problem. And sure enough, that's exactly what we had there. And they multiplied the x times x squared plus d plus 2 like you suggested we did. And we did. Okay. All right. Their next step was, if I can see this. Goodness, my stomach is growling. Okay. And they broke this into 2x over this, plus 1 over that, plus dx over that. This used a use substitution, which gave us that, remember? Okay. And then gave us this one. Okay. So we did those steps. And lastly, not lastly, but in our process, and for some reason, my cursor goes out. I don't know why. Okay. Now it's back. This was our angle, and we had it because the tangent of theta was at 2, so we did everything there. So that enabled us to do our sine and our cosine without having to use a bunch of trig identities. We have it there on our triangle. Oh, all right, and that's the last slide. Conceptual insight, in case you had any. The examples in this section illustrate the general fact, and this is pretty key. The integral of rational functions, like we've just been doing, can be expressed as a sum of rational functions. You saw in that last one. Oh, they never wrote down the answer, and I erased mine. So, but if you look just above there, there's some rational functions. 1 over 1 minus 1/4 x over x squared plus 2. That's a rational function. Okay. Arctangents, there we had an arctangent in it. Of linear or quadratic polynomials, we had arctangent of a linear polynomial, but you could have had quadratic in there. Logarithms, and the first one was of a linear, and the second was of quadratic polynomial. Other types of functions, such as exponentials, trigonometric functions, and the other trigonometric functions do not appear. Inverse tangents, rational functions, logs, and the inverse tangents and the logs can have either linear or rational or quadratic, but never anything beyond that. Pretty nice, huh? Now they have a thing about computer algebra system. If you have access to this, you can go back and do it. It would be, I guess that stands for a partial fraction. Okay, so anyway, that's what you use. Any questions on 4 or 7.5? You want to do preliminary questions? Yay or nay? Yay, okay. All right, so let's shrink this down and let's do them here. Suppose that the integral of f of x, can't write, dx is equal to log of x plus the square root of x minus 1 plus c. Okay, we know that's an answer. Can f be a rational function? Yay or nay? Why not? Yes, it was multiple choice, yes or no. He goes, no, yes, and he was right, but why? Well, that conceptual insight we just had, what was that? It can be expressed as logs, got it? But it said rational functions. Said nothing about radical functions. No, can't be. So that is not. We don't even know what it can be, but it can't be a rational function. Look back again. Sum of rational functions are tangents of either linear or quadratic functions, and logarithms of either linear or quadratic functions. That has a log, but there's nowhere in there that it say radical functions. So no, that was a no. Number 2. Which of the following are proper rational functions? A is x over x minus 3. Proper or improper? Okay, improper. Remember, if that was 10 over 7, would that be proper or improper? Why? Numerator is greater than or equal to the denominator. Well, here you do it with degree. The degree is equal to the denominator. It has to be less than. Okay, A is improper. B is 4 over 9 minus x. That's proper. Okay. C is x squared plus 12 over x plus 2 times x minus 1, or x plus 1 times x minus 3. Proper or improper? Proper, because the degree of the numerator is 2, the denominator is 3. Okay? How about D? 4x cubed minus 7x over x minus 3 times 2x plus 5 times 9 minus x. What you think? Why? Degree of the numerator is 3, degree of the denominator is 3 also. Have to do one long division, then you'd be able to proceed. That means you have to multiply all the denominators together, divide into that numerator, get your quotient, do that integration, then with the remainder you can do a partial fraction. Sounds like fun, doesn't it? Okay, which of the following quadratic polynomials are irreducible? X squared plus 5. Is that irreducible or not? Second? Yes, it is irreducible. How about x squared minus 5? Second? No. X plus 5 times x. X plus radical 5 times x minus radical 5. Remember, you can have radicals in them, you just can't have i's in them. That first one, you would have an imaginary part. The second one, you can have a radical part, but you don't have any imaginary part. So that one can be, that's not irreducible, okay, in the real number system. That's what they should be saying also. How about C? X squared plus 4x plus 6. What you think? Say again? No, it's not irreducible. What do you mean? Is it irreducible or not? No, it's not irreducible. Okay, and why? Huh? Is it? Say again? You can't reduce it.
No, because if the 6 was a 4, then you could.
Okay. Yeah, for sure that. What did you use to gauge that on?
6. I get 6, either 6 and 1 or 3 and 2.
Okay, you're trying to factor, right? Remember, you can use radicals. Here's the best place to go here. Remember our good old discriminant. We usually try not to discriminate, but this time we will, okay? In the quadratic formula, b squared minus 4ac. Think of that, okay? What is your b? Okay, b squared would be? If b is 4, b squared would be 16 minus 4 times 1 times 6. And guess what? You're right, it's irreducible. The reason is 16 minus 24 is negative. It's not that you can't factor it, it's that it would do this. You could have done the same thing here. Your b is 0, b squared is b0 minus 4ac, that'd be minus 20. That's what. Minus 4ac here, plus 20. Yeah, you could take the square root of plus 20. It's not. It's an irrational number, but you could do it. Okay? So that's what you do. Think of your discriminant. Okay, how about the next one? D. X squared plus 4x plus 2. Is it reducible or not? It is reducible because it'd be 16 minus 4ac 8. So yeah, square root of 8. You can take a square root of 8, it's just not. It's an irrational number, but it's still fine. So, which of the following are irreducible? A and C. Okay, let's see what the back says. The square is already completed, irreducible. Okay. Yeah, the second one is not irreducible. It was reducible. The second one was irreducible, and then the third one is, yeah. Now, they carried it on out and did completing the square. They didn't ask you to do that. They said, well, let's see. It says to check, complete the square if necessary. So you could have done that. All you have to do at this point is just do discriminant. And if it comes out positive, it's reducible. If it doesn't, it's irreducible. Comes out negative, zero. Okay, number 4. I think I'll erase all this ink, if that's okay. Let P over Q be a proper rational function. P over Q proper. Okay, rational function. Where Q of X factors as a product of distinct linear factors, Q is X minus AI, blah, 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 blah. Okay, those factors. Then, the integral of P of X over Q of X dx, and it says choose the correct answer. A is the sum of logarithmic terms. And that would be a sub I times the ln x minus a sub I. Okay? For some constant AI. So these are various constants. B may contain a term involving the arctangent. Okay, which of those is true?
B.
Why?
The other one's not true.
Because what? A is not true? All right. Wrong. Okay. Okay. Because, remember, it says those can be linear. It said Q can factors as a product of distinct linear factors. The only way you get an arctangent is if you have a quadratic factor, irreducible quadratic factor. So since these are all linear factors of Q, then there's going to be sums of logs. The only way you get the arctangent is if you have a square term left in the denominator. Okay? So I contend A. Okay? But you may be right. Let's see. 4 is not in the back of the book. Okay. I'm right. Okay. We'll settle that. Okay. Okay. Homework exercises. Do number 1 for sure. It's matching the rational functions with the results of that. Okay, so I would definitely do number 1 and or 3. You can do 3 instead if you want to, or both. Any of the either 5 or 7 or both, and any of the odds 9 through 45. Okay, any of those. There's a bunch of them. Either 47 or 49 or both, and any of 51 through 57. Okay. So, any questions on 7.5? Any? Okay. So let's go on to 7.6. What's that?
Did you say we were just kind of going over one of them?
Yeah, that's the next one. I thought it was going to be this one. I forgot this one was in here. I don't know why this isn't coming up. Okay, I'm going to back out of this and do, whoa, ha, this is what I thought. 7.6 was not in the old edition. So 7.6, I don't have slides for, okay? I was afraid of that. I knew there was something weird going on here. So let's just go through using the text here, and I think I'll go down and use a almost blank slide like this. That one would be better. Okay. Now, way back in chapter 5, which we kind of began, and in the preceding sections of this chapter, we've seen a variety of techniques for evaluating various integrals. Okay? Often the integral comes from a particular application of calculus, definite integration, or whatever, you know. In general, there's no hard and fast rules for evaluating a given integral. But there are some various heuristics, whatever those are, that help us determine which technique are most likely to apply. All right. Given that we have an integral, I didn't realize this wasn't being shown. Okay, now we're showing. Okay. Given that you have an integral, this has nothing to do with what's on the screen here at all. I'm just using the white space. The integral of f of x dx. Okay? Here are some steps one might apply to try to compute it. Okay? One of the first questions you ask yourself, do any algebraic simplification, it's not a question. It says, do any algebraic simplification possible? Okay? For instance, if you had what looked like a rational expression, you know, rational function, if you can factor that thing and eliminate something from numerator and denominator, do it. Make it simpler. Okay? So do any arithmetic simplification possible. Cancel terms, I don't really like that. Divide out terms if in fractions were possible. So let's show some examples of that. Okay? All right. What if you had this integral? X cubed minus 1 over x minus 1 dx. What would you do? What technique would you use?
Or it's improper, so.
It's right. It's improper. So what would you do? Raise your pinky when you drink your tea. That makes it proper, right?
Split it up.
How?
You could. Same problem with not or is that?
Say that again.
Because they both have x minus 1 in them.
Okay. What you mean? Factor the numerator? Is that what you're saying? Or how do you? What do you mean?
Like the numerator and the denominator both have x minus 1.
Okay. The numerator is x cubed minus 1. What do you mean it has x minus 1? That it factors out of it? Is that what you meant?
It divides out.
It divides out.
Yeah.
Okay. And how did you do that? Long division, or did you factor it? That's what I'm asking. How did you determine that? Just what the book said? Oh, no, not that.
What's the factor of the numerator?
Okay. Do you know how to factor the difference of two perfect cubes? Sure you do. How? You may do. I'm sort of making fun, but you might know this exactly. You're right. It has a factor of x minus 1 in it. But do you know what the other factor is? Oh, no. That's what I was afraid of. Okay? Sum or difference of two perfect cubes, here's what you do. Okay? You're right. It has that. Take the cube root of this, same sign, cube root of that. Okay? So you're right. That is a factor. The second factor, though, is, forget about this one. Take the x minus 1, square the first term, x squared, opposite the product of the two terms, plus x, square the last term, plus 1. That's how you factor sum or difference of the two perfect cubes. Okay? You remember that from a long time passing? You do. Or you can divide it like one was suggesting. Let's do x minus 1. Or can we use synthetic division here? Okay, I'll show you in a second. Let's do long division first. How do you do that? The denominator goes outside the house. What goes inside the house? And how do you write that? X cubed plus 0x squared. Excellent. Excellent. Next. 0x minus 1. Exactly. Okay? And now you divide. X will go into x cubed how many times? X squared times. Then you what? Multiply. X squared times x is x cubed. X squared times minus 1 is minus x squared. Then you do what? Change signs and add. So you make that minus, that plus, and add. What do you get? X squared. Bring down the 0x. Now, divide. X will go into x squared how many times? Plus 1 plus x times, you're right. And then multiply. X times x is x squared minus x. Then you, yes, good
You're a
thing.
math teacher, right?
Yes.
You know Mr. Sanders?
Do I know what?
Mr. Sanders.
Mr. Sanders.
Electric teacher.
Yeah.
Is he down this way?
Yeah. Okay. I don't know if he does it there or not, but if he is there,
I know, bro. I just gave up, bro.
what's that? Okay, let's do the whatever. X minus 1. Okay, change signs and add, right? And you got x minus 1, and that goes plus 1 times. And that's exactly what we got there. Okay. Now, want to review synthetic division? Yes, it's real easy. Okay? Here's the difference. Notice we changed signs and added every time. And we never used the x's, did we? They just all canceled out here and here and here. I mean, they all, x minus 1, they cancel out there. So we really didn't use them. So what we do is put a plus 1 outside. Okay? Opposite whatever that one is. Okay? Now, you put your coefficients, because we really didn't use the x's anyway, right? Our coefficients were 1, just like we had before, 0 for x squared, 0 for x, and minus 1 for the other, right? Okay? Now, you'll never see this in a book. I've never seen it. Skip a line, draw a line. Okay? Pretty easy, right? Bring down the first one. From this point, you multiply and add. 1 times 1 is 1, and because you already changed signs, you add. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Minus 1 minus 1 is 0. There's your remainder. Then you fill in your coefficients again. You drop it by 1. X squared plus x plus right? That's a lot easier. When can you use synthetic division? Anytime? No. When your denominator or your divisor, the coefficient's 1, exponent 1. Only time you can use that. If it's of the form x minus a, then you put an a out there. If it's x plus a, you put a minus a out there. But it has to be a naked x there. Coefficient 1, exponent 1. If that was x squared minus 1, you can't use it. If it was 2x minus 1, you can't use it. Only use it when it's x plus or minus something. And it's pretty short and sweet. Okay. So there we have done that. All right. So let's erase all this other stuff. Okay. All right. Whichever way you got to it, you see all you have left is that. The integral of x squared plus x plus 1 dx. And can you integrate that? How? Let's see. Good deal. Done. All right. The B one. Here we have an integral that's x minus x cubed over the square root of x dx. How would you proceed there? Okay. What do you mean by that? Is that what you meant? Okay. Done then? No. Square root of x to the top. What you mean? Can't hear? Is that your final answer? It should be. Okay. So you're saying x times x to the minus 1/2? Is that what you're saying? Okay. All right. Minus the integral. And what would this one be? Okay. And what was that multiplied to? Yep. Oops. Minus. Yes. Now, a couple ways you could do that. I could hear sort of what you were saying. You said x is 2.5 and 2.5 is 5/2. Or you can think of this as x to the 6/2. 6/2 minus 1/2 is 5/2. So either way, it gets the same answer. Dx. Huh? Oh. Good luck with that. Okay. All right. And what would that give us? I'm going to erase some stuff. We already did this, so I'll erase it. What did that first integral give you? This one down here. X to the what? Integrating that. The 3 halves over 3 halves, which is the same as multiplied by 2/3, right? Got it? Okay. Minus
Anything else?
7 halves times 2 sevenths. One more. Plus C. All right, good deal. I don't think they carried it all the way, but yeah. It just says, which can be easily integrated. So I thought, let's go and easily integrate it. Okay. Let's do C, which is yes in Spanish, okay? Let's go and erase this. And we'll do the integral of 1 over sine squared x dx. Okay, what do you mean moving it to the top? Tell me what you mean. Oh, sine to the negative 2? Is that what you meant? I would actually, in a sense, move it to the top, but what the book suggests is, what is 1 over sine? Cosecant. That's the same as cosecant squared. Okay. But the good news is that is a perfect antiderivative. Derivative of something is cosecant squared. Huh? Okay. What if that would have been the integral of secant squared? Is secant a perfect derivative of something? Secant squared a perfect derivative of something? Thought we just did it not long ago. Derivative of tangent is secant squared. So derivative of, put a co in front of it. Cotangent would be negative cosecant squared. Factor of minus signs. I don't know if you find this helpful or not, but to me it is a little bit. Here's our trig functions. Sine, cosine, tangent, cotangent, secant, and cosecant. Okay. Derivative of sine is cosine. Derivative of cosine is minus sine. We remember our minuses, don't we? Derivative of tangent would be secant squared. Okay. Derivative of cotangent would be minus cosecant squared. Okay. Derivative of secant theta, this is all with respect to theta, okay, would be, anyone remember that one? Yes, secant theta, tangent theta. Secant theta, tangent theta, and derivative of cosecant with respect to theta would be note the pattern. For your cofunctions, their derivatives are always negative. And then it would be cosecant theta, cotangent theta. Okay? So, this goes back to this one. So, the antiderivative of cosecant theta would be negative cotangent theta plus c. Okay. All right. That's a little different from what I usually I don't go to the cofunctions. I don't go to the secants in the higher levels. But in this case, it just worked out so easy to do that. Otherwise, yeah. Well, because the derivative of cotangent is cosecant squared, the antiderivative of cosecant squared is minus cotangent. Right? One undoes the other. Okay. And of course you remember these two, don't you? With the signs, SIG and signs. All right. Let's do, oh man. We can't do D. We ran out of time. Thought for sure we were going to. So let's start next time with D. 1D, and then we'll look at some of the others. Let's see if there's enough here that you can do some homework exercises on. You can start looking at some of the odds 1 through 9, but we haven't done enough, I don't think, to do them, but see if you can. All right, good deal. All right, you were asking, or you suggesting, we are going to do 7.6. This was in this section. They added this. It wasn't in the lesson. The improper integrals, I'm just going to tell you about pretty quickly, but you aren't going to be responsible for it on the test. Okay? We'll just go through a slideshow on that. We'll also do the same thing with probability and integration, 7.8. Okay? But 7.9, we will do a little bit of 7.9. So we'll skip mostly 7.7 and 7.8. I'll do a slideshow just so you're exposed to it if you ever need it. But then we'll do numerical because you do wind up needing that sometime. All right. Any questions?